right, let's talk nitration. So, I want you to take a minute and just jot down from the last video what were the 3 steps that we took to go from benzene to either bromobenzene, or whether it was chlorobenzene or iodobenzene. Doesn't matter how we generated that first step. I may have given you a hint, generation of something, right? So I want you to take a moment to just write down the 3 steps, because we are going to use those in all of these reactions. So it's going to be kind of like a repetitive theme, and I want you to come up with what those steps are. So pause me and write down the 3 steps, and then let's see if you came up with the 3 correct steps that we need to take. You should have written down generation of a nucleophile or electrophile? Electrophile. Attack of the nucleophile, so that is your aromatic nucleus. And re-aromatization. And a lot of times students do ask me, they say, am I supposed to write this down in a test setting? I will tell you one thing. When you are writing down the mechanism of your, each of your reactions, when you're putting it together, it's a lot simpler, a lot easier for you, and more channelized and more focused when you are kind of organizing your thought process, that this is what you have to do. Especially if you haven't had a lot of experience with mechanism writing in Organic 1, having that train of thought goes a long way. So if I were you, if I was in your shoes and this was my situation, then I would absolutely do that. And once you get better at that, you may not need to, do that. But especially when you start doing that, that way you have kind of like checkpoints. Okay, I showed the mechanism. So I showed the electrophile generation. I showed the attack of the nucleophile, because all 3 of those will have a specific amount of points allocated. Let's say it's out of like 4, 5, 7, whatever number of points. If you show that step, you get those points. It's as simple as that. So if I were you, I would do that. Can anybody tell me what would be the electrophile here? So what was that one quick strategy to do that? Yeah, so you look at whatever is the group and you put in a positive charge, right? So here that group happens to be NO2, and we are supposed to put a positive charge. Where do I put the positive charge? I put it on the nitrogen, and that is the point of attachment, right? Okay, so let's see how this reaction will take place and how the reaction will proceed. The reaction is being done with concentrated nitric acid, concentrated sulfuric acid, and as a side product, water gets generated as well. So I have nitric acid. If I had to write this out, I would say, well, nitric acid and if I have to write the mechanism, the best way to do that is to simply draw it out. I'm putting down all the lone pair of electrons. Here's my sulfuric acid. And if I were to now carry out my reaction, what do you think will attack? So what should be your nucleophile? What should be your electrophile? Sulfuric acid is a fantastic acid, so it loves to give up protons. If you're thinking that your proton is going to be the receiving end, that's the one that should receive electrons from somewhere from nitric acid, you're absolutely right. So it's the oxygen which is going to attack the hydrogen, one of the protons. The bisulfate is going to leave. And that will give you, and this is in an equilibrium, We are forming 3 bonds on that oxygen, so it's kind of unhappy. The bisulfate has left. Oxygen would try to get rid of its positive charge by allowing the NO2 to leave, and water gets generated. So H2O plus NO2 plus will be the byproducts. Now, H2O is that byproduct that you saw in the overall reaction as well. Now, if your glassware, when you're running this reaction in the lab, if your glassware is not dry, then what will happen? You're providing that water, right? So backward reaction will get triggered, and your nitronium ion, as it's called, nitronium ion, that will get quenched, and you're not going to get high yields. It's actually then very difficult to crash out any amount of reaction that may have taken place. So it's really important to run this reaction in a dry scenario where your glassware is completely dry as well. And that's what I'm showing here as well. In terms of mechanism, notice how nitric acid reacted with sulfuric acid, how that generates the formation of that oxonium on the or protonated HNO3, and that generates the nitronium ion species, and water gets generated as well. And now this NO2 plus is ready to rock and roll with your benzene ring. So your benzene, which is going to serve as your nucleophile, and that's going to attack your electrophile. A reaction is always a reaction between where the electrons are and where the electrons are required. And so you will end up getting the intermediate, which is right over here. And of course, this has lost its aromatic character, so it's not going to stay like that. And your conjugate base, which is your H2SO4, is going to pick up that proton and is going to re-aromatize that. So if you think about the purpose of sulfuric acid, it is actually twofold. Not only does it serve as a catalyst for that initial protonation, it actually does 2 other things. It absorbs the water molecule, from nitric acid, remember, that got generated. So H2SO4 loves water, so it's going to coordinate, it's going to react with that water molecule and protonate that real fast. And the conjugate base of the sulfuric acid, that allows that re-aromatization to take place. So it's not water that's coming out to re-aromatize, but rather the bisulfate. Okay, all right, so that was nitration. Let's talk about sulfonation. Now, it's worth mentioning that sulfonation as a reaction condition is written in 2 ways. Sometimes you may see this written as fuming sulfuric acid. Fuming sulfuric acid. It may also be written as concentrated H2SO4 and heat. And they both really mean the same thing, fuming sulfuric acid. That just means that when you open the bottle of that sulfuric acid, there should be some gas fumes that should come up. And what would those fumes be is the question, right? So sulfuric acid, by its very nature, loves to essentially absorb moisture, and even the commercial sample that you buy, which is typically 98%, over a period of time can become like a 95% and 94% and so on and so forth. And for most practical reactions, because it is such a fantastic acid, those slight differences in concentration may not affect the overall result of the reaction. But in specific reactions, sometimes you may, such as this one, where they're saying fuming sulfuric acid, that means that they want some amount of SO3. So SO3, they want that present in our reaction mix. Now, SO3 is sulfur trioxide, which you may have heard about in the past through acid rain, right? That's one of the acidic oxides that is generated by the industrial effluent, and when it reacts with the moisture in the atmosphere, it actually generates, so SO2 will generate H2SO3, SO3 will generate H2SO4, and so when it rains and precipitation happens, along with the carbonic acid, which is the actual makeup of rain, so rain is nothing but carbonic acid, you also get some amounts of sulfuric acid and sulfurous acid that come down. So in that context, you may have heard about it in your experience in Introduction to Chemistry or your general chemistry course back whenever you took it. But anyway, so here we are saying that we will have to regenerate that SO3. That means I will have to, through some means, drive this H2O, the water molecule, away. And so typically that's just basically done by heating the H2SO4 till it starts to fume a bit. So as it boils, that water is driven off and a gas gets generated. And the presence of that gas is essentially tested using litmus paper. And then it's ready to be used for the sulfonation reaction. In this particular reaction, we have SO3, so I'm going to just write that down. Note that the sulfur-oxygen bond is polar, so at any given point of time, you could say that sulfur has a positive charge, oxygen has a negative charge. And when you put that with H2SO4, what can happen? Yeah, that negative is going to pull the proton off, bisulfate will leave. So you can generate your electrophile very, very easily. Very, very easily through this reaction, through the simple protonation. Okay, now as the reaction goes further, your benzene to attack. So benzene attacks this newly formed electrophile that we just generated. Notice the attack is happening at the sulfur. That will be the point of attachment. And in the process, we have utilized the 2 pi electrons in forming the bond with sulfur. And that positive charge will be on the benzene, on the ring. That's no longer a benzene ring. This is going to be your intermediate, which is now going to lose its proton, one of the protons, to the bisulfate, which will re-aromatize then and form benzene sulfonic acid. So notice in all of these, step number 1, generation of electrophiles. Step number 2, attack of the nucleophile. Step number 3, re-aromatization. So as you are making your own notes, it's a good idea to sort of highlight those 3 for yourself as you're writing, because then as we go further, it'll be a lot easier for you to recognize the 3 generation of electrophile, to be able to write down the complete mechanism. Again, when you're seeking what should be the electrophile, simply break the bond between the atom or the group of atoms and put down the positive charge, because an electrophile should have a positive charge. Go from there. Okay? All right, once you have your benzene sulfonic acid, if you heat it with a caustic base like sodium hydroxide, typical heating will be more than 150 for sure. Depending on your substrate, this could be 150 degrees Celsius, could be higher, but it's a strong heating that we are looking at. Notice they have shown 2 steps, right? Because as a result of the first step, that SO2 gas is given off, and you first get the phenoxide, and then that phenoxide simply exchanges a proton with the hydronium ion. So the negative pulls the proton, water is lost, and you get phenol. So I would not ask you the mechanism of how we go from benzene sulfonic acid to the phenoxide, how that loss of the SO2 takes place, but just know that you could carry out the hydroxylation by a sulfonation followed by treatment with sodium hydroxide, heat, and then putting in the acid, H3O plus. That should give you the generation of phenol. So this is a good time to sort of write this down for ourselves. Let's say the question is, prepare phenol from benzene. And you could do a version of it. You could say perhaps prepare paracresol from toluene. Right? That's possible too, however you want to do that. Or an ortho version, however you want to do that. So we are starting out. So one thing that you should consider is, well, I know that phenol can be generated. So I'm going to put the retrosynthetic arrow. Notice I'm putting in the solid arrow. This is my retrosynthetic arrow. It can be generated from benzene sulfonic acid, SO3H. And that can be generated again from benzene. And that is just a sulfonation step. So we know that using a base, right, using a base on benzene sulfonic acid gives us phenol. There is an H3O plus step involved in that as well. And we also know that using a sulfonation on the benzene, we can generate the benzene sulfonic acid. Notice I'm going backwards, right? That's why the retrosynthetic analysis, as it's called. But if you have to come up with the synthesis, you will obviously go in a forward direction. So you would say that benzene will have to be treated with concentrated H2SO4, which with heating will give you benzene sulfonic acid, which after treatment with sodium hydroxide and H3O plus, strong heating is required in the process. It will give you phenol. So what I have shown in green is the forward sequence of reactions. What I showed in red was the retrosynthetic analysis, recall, in which we go backwards as to what kind of reactions or how can I prepare the given molecule from something that I know. So thinking about that, designing that is what retrosynthetic analysis is. You're analyzing, you're designing, and when you actually put the reaction conditions in place, that's the actual step that you take. All right. The final reaction that we are going to talk about is the Friedel-Crafts reaction. All right, so we have benzene with 2-chloropropane. On the arrow is AlCl3. My product is isopropyl benzene plus HCl. Anybody remember what was isopropyl benzene again? Yeah, cumene. Cumene. What is the role of AlCl3? What's on the arrow? Yeah, that's a catalyst. Can somebody tell me what would be the electrophile here? What's the nucleophile? If you're thinking the electrophile is CH3 with a positive charge, you're on track. So that's your E+. And your nucleophile should be the benzene ring. So let's take one step at a time and say how the reaction takes place. Now, when Friedel-Crafts did this reaction, it actually gave a lot of problems. So there are some problem points with the Friedel-Crafts. We will call this alkylation reaction. So this is the alkylation. That was the first one in which they essentially saw all these problems. But even then, even though there were a lot of problem points, there were some very, very big achievements that should be mentioned here. Before this, carbon-carbon bonds were pretty difficult to generate. I mean, if there is polarity, if there is a negative end and a positive end, it's fairly simple to make those bonds, right? But generating a carbon-carbon bond, people saw that as a non-polar bond, and it was difficult for them to comprehend how the reaction will take place. But just the sequence, just the use of the Lewis acid catalyst, that was remarkable, that was revolutionary at the time. But there were problem points, and so they were the ones who identified the problem, and then they were the ones who said, well, wait a minute, we also have a solution for that. So it's kind of interesting, you know, when you discover a problem and then you are also able to identify a solution for that. And we are going to discuss both of those, the problem points as well as the solution, because that alkylation, the problems that they saw in alkylation essentially led to a different kind of Friedel-Crafts, which was the acylation reaction. So let's look as to how the reaction will take place. First things first, our AlCl3 tends to coordinate with the chlorine. So the AlCl3, being the Lewis acid, tends to coordinate with the chlorine, which is the negative end anyway of the RCl molecule. So this is possible in any of the alkyl halides. It is not possible for an aryl halide or for a vinyl halide. Can you think of a reason why Friedel-Crafts would not work for an aryl halide or a vinyl halide? The hint I want to give you is perhaps the idea that you are going to generate a carbocation. So what do you think might the reason be? If you're thinking about the stability of the carbocation, absolutely you're on track. But if not, then we need to hone in that skill a little bit. So as the Cl coordinates with the AlCl3, Al is going to take away the Cl, and this carbon-chlorine bond is going to basically break. So you end up generating the electrophile that you're seeking, an AlCl4 with the negative charge. Now, you have the nucleophile, which is the benzene ring, and you have the electrophile, which is the carbocation. Your two electrons are going to go from your benzene onto the positive charge, and that's going to generate the formation of your intermediate, right? And so the negative end of the molecule from the AlCl4, so it's essentially again a coordinated species, and since AlCl3 is a catalyst, it's going to get regenerated at the end of the day. That Cl negative is going to pick up the proton. Electrons are going to move on top of the benzene ring. You end up getting your cumene as your product. Okay, HCl and AlCl3 are your side products. So if we were to do this reaction in the lab, since HCl is getting generated, would you want to run this reaction in the hood or in the bench space? Yeah, please run that in the hood, because you are generating HCl. You don't want to inhale that. That is going to give you burning sensation. So yes, whenever we have the Friedel-Crafts reaction, you would want to run that in a hood. Okay, all right. So couple things here. Like I said, your electrophile is going to be the carbocation, so that is carbon with a positive charge. So anything which just does not generate that, such as the vinylic carbocation, recall, is only a theoretical concept. Some people don't even believe that it exists. In fact, experimentally, it has never been isolated. especially if you're talking about the primary vinylic carbocation. So that is the reason that aryl halides and vinyl halides are not going to react. That means you would never be able to perhaps use chlorobenzene with benzene and AlCl3 to form biphenyl. This reaction would not work because you would not be able to generate the carbocation from the chlorobenzene. Okay. Another problem that was seen was the case of linear chains. So for instance, if you had to convert, let's say if you had to generate from benzene perhaps propylbenzene, so that's a linear chain, right? It contains 3 carbon atoms. You have probably already identified that the electrophile should be the chloropropane. AlCl3 is my Lewis acid catalyst. My first step would be my chloropropane interacting with the AlCl3. Recall that this carbon-chlorine bond is a polar bond. And we are leaning towards the generation of the formation of a primary carbocation. And your teacher in Organic 1 must have told you that if you get a primary carbocation, then you have to ask a question. What is that question? Is this the most stable carbocation? That's the question. So is it? No. Why not? Because you do have 2 hydrogens right next door, which they can migrate, right? And if they rearrange like that, anybody remember the name of that? 1,2 hydride shift. Good job. That will generate this secondary carbocation. Which of them is more stable? Absolutely. The secondary carbocation is approximately 500 folds more stable than the primary. Does that mean that the primary will not work at all? No. One will be your major product. The other is going to be the minor product. So one is going to give rise to attack taking place from the benzene ring. And so, of course, over, the whole 9 yards, you get the secondary position. The Cl minus will pick up that, and you end up getting cumene. That will be one product. Another product would be that the benzene attacks propyl chain is now going to get the substituted location, and your Cl minus will give you propylbenzene, much the same way. So we are trying to suggest here that benzene doesn't have eyes, right? It's just a source of electron. It's not going to just say, hey, I'm not going to react till that secondary carbocation is going to get formed. It's just going to see if there is 2 molecules that are in close vicinity that the reaction can take place, then the reaction in yellow totally feasible. But that's not the only reaction. A lot of that primary carbocation will find the necessary reaction conditions to get converted into the secondary carbocation, and hence the one in red is going to be the more stable, the thermodynamic product. And so keep in mind, this probably will go in the ratio of perhaps 70 to 30, making the propylbenzene the minor product, not the major product, and the cumene your major product. So what we are suggesting here is that if you wanted a linear chain, there's going to be a problem. The problem is that your starting alkyl halide, which forms a primary carbocation, will have the potential to rearrange, and hence it will give rise to two different products, which is a problem point. Another problem point that could occur is because alkyl groups they push electrons through the sigma bond, they are going to enrich the benzene ring somewhat. So they're not going to stop at one level of substitution, and actually it's going to lead to polysubstitution within the reaction. Can you stop that? That was the question. So two problems that come from here are, one is the problem of rearrangement. The other is the problem of polyalkylation. So we have identified overall, if you think about it, we identified three problems. We identified this vinylic halide. We have identified that problem, that is a bad position for the carbocation. Same reason for the aryl carbocation. Those are not stable. So this is a problem of the kind of alkyl or aryl halide that might be used. But the other problem we identified was the problem with the mechanism in which rearrangement might be possible, or polysubstitution might take place once the product gets generated. What was also seen was that Friedel-Crafts reaction was very sensitive to the availability of the reaction. What that means is that any deactivating group, so if there is a group which takes away electrons from the benzene ring, let's say you have a cyanide, right? Nitrogen is electronegative, will pull electron towards itself, that will pull electrons towards itself. Overall, electrons are being driven away from the benzene ring. So anything that's listed here essentially, which is not in parentheses, not those ones, but anything that's outside, that will not allow a Friedel-Crafts reaction to take place. So there were restrictions on the substrate as well. So restrictions on presence of electrons on benzene ring. That was a problem point. So we identified four problems. Let's write them down somewhere. We have the problem of rearrangement of carbocation. We have the problem of polysubstitution. We had the problem of deactivating groups, deactivating substrates do not undergo reaction. And we had the problem of vinyl and aryl alkyl halides not reacting. Those were the ones that we have discussed. Here the question is, draw the mechanism for the electrophilic substitution of benzene by 2-chloropentane. So we have benzene. We want to react it with 2-chloropentane. 2-chloropentane means, is it a linear or is it a branched alkyl halide? Yeah, it's branched. So do you think this will undergo the reaction, or do you think it will undergo do you think it will undergo rearrangement? Yeah, this doesn't have room for rearrangement if you think about it. So step number 1, AlCl3 is going to coordinate with the chlorine and it's going to now generate the carbocation. Is this carbocation the most stable? Yeah, absolutely. So how does the reaction take place? Attack takes place. That is the most stable carbocation. One side has a primary center, so it's not going to go from secondary to primary, right? The other side is also a secondary, so no reason why there should be a hydride shift. Really, no reason. There is no gain of energy that you're going to, or gain of energy profile, energy index that you're going to achieve greater stability. It's not going to happen. And you would just simply end up getting this intermediate. And now your Cl negative is going to pick up the proton and give you the product, and you're done. That's it. The problem again lies in the linear chain. So instead of this methyl branching off, if that was a part of the rest of your chain, that is when it's going to go through a rearrangement process for sure. Okay, let's go over some more molecules so that you kind of get a feel for how the reaction takes place. So multiple substitution. So let's say if we have 2-chloro 2-methylpropane. So this is what we have. 2-chloro 2-methylpropane. That's how we are drawing it. It's going to coordinate. You're going to get what? You're going to get now a tertiary carbocation. Do you think it's stable or do you think it's not stable? It is very stable, so it's not going to go ahead and rearrange. No, not at all. And so when the reaction takes place, it is going to form as a first step and you can really use any of these bonds again. The Cl minus will pick up and you will end up with your T-butyl group on the benzene ring. Now the thing is that your T-butyl group that you have just put together is not going to stop here. It's going to send electrons through the sigma bond. So due to hyperconjugation, it's going to make this benzene ring enriched. So the reaction is not going to stop here and is going to actually go through another round of Friedel-Crafts. And the moment that first molecule gets generated, more and more reaction can take place, and your major product actually is this di-substituted molecule. Anybody, can anybody think why is it that it is the para position which gets enriched and that's the one that gets generated here? Yeah, because T-butyl group is so big. Notice, recall that typically alkyl groups, the induction that it causes, it is going to die down with distance. So while typically it's the ortho position which is more predominant when the reaction will take place, because the para position is completely out of the way because of steric reasons, you're going to end up with that particular substitution as the major product. All right, let's take a look at a couple more. Over here, I have a reaction of benzene with 1, 2, 3, 4. So chlorobutane is what we have. So hopefully you are seeing what I want you to see, that when AlCl3 coordinates, you end up getting a primary carbocation which can, you got it, it can rearrange through a 1,2 hydride shift. As that takes place, you now have opened up your nucleophile, which is the benzene ring, to attack, at the carbocation. So your major product is going to be with the branching, the secondary position attacking, and the minor product is going to be just butylbenzene. That will always be the case. So rearrangement can happen through the 1,2 hydride shift. Sometimes it can happen through the 1,2 methyl shift. Let's take a look at another one. So we have 1-chloro-2,2 dimethyl propane. Now when that coordination that I've been referring to, when that happens, of course your first carbocation possible is going to be this. Now there are no hydrogens, so you can't carry out a hydride shift. What you can, however, do, since all three are methyl groups, one of these can move. So let's number them. It sometimes just helps to number things to see. So when that 1,2 methyl shift, in this case, when that happens, what is the bond that you're breaking? Hopefully you can see it's the 2,5 bond that you're breaking, and it will be the 1,5 bond that you will be making. So I'm going to keep the 4, 2 and 3 as is. 2 is connected to 1 and 1 is now connected to 5. So I broke the, maybe I can draw it on this side just so you can see it better perhaps. So we used to have a connection between 2 and 5, right? We broke that bond and we made the 1,5 bond. So we broke the 2,5 bond and we made the 1,5 bond. Let's get rid of it so we can have that clean. And now your positive charge is going to, for that reason, it's going to be at position 2. So that's where your benzene will attack. Ta-da! And you get your product after your initial your Cl minus is going to pull off the proton and you get your product. Okay? Let's take a look at a couple more questions to see if we can apply this. The question says, which of the following alkyl halides would you expect to undergo Friedel-Crafts reaction without a rearrangement? So it should not undergo rearrangement. I don't know about you, but when I look at just molecules with their names, I am tempted to draw them out. Yeah, that's when you can see. So convert this English into the chemical language. That's chloroethane. That's 2-chloropropane. That's 1-chloropropane. That's, so again, emphasizing on the numbering, that will go a long way. A lot of times I see students would make that as this molecule and it is not. So keep that in mind. And then chlorocyclohexane, of course. Notice that the carbocation that you will get in the first case is going to be a primary carbocation, and it doesn't have any other space to undergo a rearrangement. You can't carry out a hydride or a methyl shift, there's no methyls, to give a more stable carbocation. So this is not going to undergo rearrangement. So I'm going to put a little bit of a check mark there that is one of our choices. 2-chlorobutane. Notice that this is now the most stable carbocation possible, right? So it doesn't have to rearrange into something less stable. So that also is going to be one of the ones that will go through without a rearrangement. 1-chloropropane, that's going to form a primary carbocation. That's like written all over the place. A hydride shift is likely. So that will undergo rearrangement, and so would the next one. We actually just solved this one because it will generate a more stable, right now it's a primary. After a methyl shift, it's going to give rise to a tertiary. So that will also undergo rearrangement. And the last one, which is chlorocyclohexane, is going to lead to the formation of your carbocation at the secondary position. So that too is going to be something which will not require rearrangement. Okay, so those three are the ones that you will not see a rearrangement for. On the other hand, everything else, the other two remaining, that will go rearrangement. So just to kind of summarize, it's important to recognize here that only alkyl halides can be used. You cannot use the vinyl halides. You cannot use the aryl halides. It's important to recognize that because they do not form stable carbocation. So that was one thing. This will not occur if you have electron withdrawing groups, right? So if you have things like a C double bond O or a C triple bond N, I'm going to remove the amino and I'm going to call that ammonium. I think that's a typo. And so that will not take place either. It also had a problem of polyalkylation, so many R groups getting generated. So one R, another R, and I gave you some examples of that. Rearrangement can take place, the 1,2 hydride shift, as well as the 1,2 methyl shift, to give you the more stable carbocation. And that's an important one. You must know the mechanism of this. Absolutely, especially in those that will require some kind of a methyl shift or hydride shift, because that's an added step. So for 5 points, I could ask you to show the mechanism of, let's say, starting from toluene, using 1-chlorobutane, how do you get sec-butyl, para-sec-butyl toluene, okay? And so you should then go through the steps to do that. These were the problem points. The solution to that came from Friedel-Crafts, and they suggested that we can get rid of some of these problems if we just change the nature of group that we are adding. So one thing that they said was, well, instead of bringing in a group that will enrich our benzene ring, what if I put in like a ketone, right? Now ketone is going to pull electron density, and they had already seen that once you put a ketone, ketones were not susceptible to Friedel-Crafts reaction. They would not go through. So they asked, if we do this, then this problem of polyalkylation, we can get rid of that, right? So that was one problem, so one solution. Another thing that they suggested was, and that was probably mechanism based, that if your intermediate is going to be stable, then automatically it may not want to rearrange, right? So that was another thing that they had in mind. Of course, when it comes to alkyl halides, you can't quite control that. I mean, that's a given thing, that for the reaction to take place, if you're not using alkyl halide, you are using something else, so that problem would automatically go away. But things like using cyanobenzene and not getting the reaction, that just deals with the substrate, and that was a scenario that could not be answered. But the other problems were actually taken care of by their suggested Friedel-Crafts acylation. Okay, so let's take a look. Friedel-Crafts acylation. Acyl means that you will have a RCO. So C double bond O and some R group. We saw in chapter 15 that this R, if that is hydrogen, then you would call that a formyl group. We also saw that if it is a CH3 C double bond O, we will call it an acetyl group. And if that is a pH, like a benzene ring, we will call that a benzoyl group. So keep that in mind. In general, of course, we call it acyl, but there could be different kinds of acyl: the formyl, the acetyl, the benzoyl. Now, as the reaction takes place, I'm going to number some carbon atoms. I have benzene ring. Notice the first step is still going to be the activation of that acyl chloride now with AlCl3, and that's going to remove, it's going to take away that chlorine. So as a product, we are saying that the chlorine is going to go away. It's going to leave. That means you are going to generate acylinium ion, carbocation. Is there anything special about this acylinium ion? Yeah, there is. Starts with an R. Resonance. You can totally donate those lone pair of electrons for oxygen, and yaha, I'm not saying that that's going to be the most stable resonance structure, but who cares? It's still there, right? You can't negate that either. There is a major and there is a minor, but that resonance is stabilizing this. So basically we are suggesting that the carbocation that you are generating is going to be a stable one. So it doesn't have to rearrange, and that's a good thing. So no rearrangement, we got rid of that, okay? As we have generated this, the next step will be the attack of the nucleophile onto this. Let's take a look. So we had benzene ring, we generated this acylinium ion. So attack will take place. Of course, oxygen will pull the electron back. My intermediate is going to look like, notice my point of attachment is going to be position 1 with the double bond O. 3 carbons connected to that. You have a positive charge. And now your Cl minus comes back, picks up the proton, and voila, you get your ketone. So let's see if out of the 4 battles that we had, if we won another battle or not. One battle that we won was the problem of rearrangement, right? We said that no rearrangement here, since carbocation is resonance stabilized. There is no requirement. I'm going to put that in the thought bubble. The fact that this is a ketone, and that means that the oxygen is going to pull electrons towards itself and also away from the benzene. What does that suggest? Yeah, that it cannot engage in another subsequent substitution. So can poly substitution be seen? No. No poly substitution. And that's a good deal as well, because that means that you have only one single product, right? So that's another one. I'm going to put it in another thought bubble. Third one. Recall, one problem was the use of vinyl halide or aryl halide. Well, we are not using that anymore. It's not alkylation, it's acylation, right? So just changing the substrate has pretty much changed the nature of reaction. So that's not even a problem anymore. The only thing which we can't control is that if you use cyanobenzene, this reaction is not going to cut it. But we were able to eliminate three major issues from there. And the yield that you get, since you get only one single product, this reaction is a pretty high yielding reaction, typically more than 90% or so. But you might question, wasn't our purpose, wasn't our aim to go from benzene to propylbenzene, because the linear molecules had the issue? And the answer to that is absolutely. We can subject this ketone to a reduction reaction, just basic hydrogen palladium reduction reaction that you learned in Organic 1. This benzylic position is super reactive, and that can give you the propylbenzene, which is also a very high yielding reaction. So even if you were to run these two sets of reaction, 2 hours for the first reaction, maybe about 15 minutes for the second, probably in about overall, let's say workup, reaction, everything, characterization, in about 4 hours time, two mutually exclusive events of 90% each, you're looking at around 81% yield at the end of the day. On the other hand, if you recall what we got in case of our first attempt on Friedel-Crafts alkylation, in that case we had pretty low yields. In fact, we used to actually have a lab in which we would have like 8 or 9 peaks in the GC. Even though we would expect that perhaps we would get like 3 or 4 products, there were so many side reactions that the yields were like no more than 20 to 30%. So pretty bad yield in that case, pretty bad outcome in that case, because if my purpose was to generate, let's say, a scaffold which is used to develop some pharmaceutical drug, and I need 1 gram of the starting material, I will have to use the same reaction. I will have to run the reaction like 10 times, right? To be able to get that. Now somebody could say, well, why can't I run the reaction if I know that only 20% of it is going to be any good? I could simply just run the reaction on a larger scale. Also, no. A large scale reaction will come with its own complications. Sometimes some reactions could generate a lot of heat and might be unsafe. So you can't just, oh, I'm just going to run the reaction on a larger scale. It may catch fire, it might be unsafe, it might generate a lot of waste product, it may not be economical to do so. And so you can't just do that. And so having an alternative which rather gives you better yields is a much better deal than otherwise. So how would that take place? And that's what I'm showing you here, that we have essentially the acylation of the benzene, which in the first step is giving you the ketone, and then that ketone is being subjected to reduction, which is what I was trying to explain. Both of these are high yielding reactions, and so the overall product is going to be pretty, product yield is going to be pretty. And here's your reaction. We are showing the formation of the acylinium ion or the acyl cation. And notice how we've shown the resonance stabilization, which is going to cause the formation of the reaction. I don't like that arrow. It seems like something happened in the formatting. Which shows the formation of our ketone. Notice in this case I had only 2 carbon atoms, and so I am going to end up with acetophenone at the end of the day. It's important to recognize that the point of attachment is going to be the C double bond O containing carbon atom. Once in a while, maybe I would say about 15 to 20% of the time, students would write this mechanism as, like, I would ask them, here's your benzene, here's your acid chloride, AlCl3, and show me the product, and they say that the product is, I'm going to try to put that together. My hands always freeze to do that. This. Is this right? It's wrong at many levels. Let me tell you why. It's wrong on many levels because this was supposed to be a methyl group, right? And how many bonds is this carbon making now? It was making 4 and now it's making the 5th one. Really? Pentavalent carbon? Bad idea. And this carbon, which actually does have the positive charge, you're showing only 3. Not cool. So please, if your hand is trying to draw that, check the Lewis structure. That's why I keep saying and keep reminding you, when in doubt, draw it out. Number your carbon atoms, bring the negative to the positive. Just 2 rules which go a really long way in writing the correct intermediates as you go.